Grade 9s. Today we're going to do 7.4, which deals specifically with similar triangles. 7.3, we went through similar polygons, and as we said, polygon just means many and gon means sides, so many sides. This time we're just doing triangles, so it's just going to be 3 sides all the time. So essentially it's probably easier than 7.3 because we only have to worry about 3 sides, and the rules and the laws are exactly the same. So a triangle is a special polygon. When we check whether they're similar, we have to have the same things we needed before. We needed to have the same interior angles between the two triangles, and we also have proportional lengths, which means the ratios of the lengths have to be the same. And we're just looking for the scale factor, right? If you divide PQ by ST, you should get a number, and that number should be the scale factor, and that scale factor should be the same as if you do QR divided by TU, or PR divided by SU. If we get the same scale factor, or the same ratio, for all of those sides, and we know the angles are equal, then we must say the triangles are similar. Now here's an example right here. We've got two triangles side by side, and we know they're similar, because this angle is equal to this angle, or not equal to, well, it is actually equal to. This angle is equal to this angle. So they might not be pointing the same direction, but they're still similar triangles. And this angle is this angle. So we know that the 3 angles are equal, and that's part of it. What we need to know is that do the corresponding sides, are they equal? So if I look at B A divided by what would be, it's between the 75 and the 62, so between the 75 and the 62 would be RQ, or QR. Okay. And that needs to be equal to AC, which is between 75 and 43. So 75 and 43 needs to be the same as PQ. And that needs to be the same as, which one didn't I do here? RP. So that, nope, I did BC is what I'm missing, right? So BC would be between 62 and 43. So 62 and 43, that would be PR. Okay, so all of these have to be equal. Now, keep in mind that we've got over here, AB corresponds to QR. Well, AB, okay, that's the same thing as BA to RQ, okay? It doesn't matter if you write AB or BA. It's the same line, right? AB can go this way and BA can go the other way, but it's exactly the same line. So make sure you don't, it doesn't matter if you get the letters in the wrong order, but it does matter that you're referring to the right line. If you refer to this line as BC, that's correct. If you're looking at this line and you refer to it as BC, then it's incorrect, right? That has to be either CA or AC. So just be aware of that. The letters might be in different orders, but it might mean the same thing. So for instance, this over here, BC, really could be written as CB to PR. And this one could be written as CA to PQ. So the sides, just keep that in mind. Are these similar triangles? Justify your answer. Okay, so what it's asking right now is there's a triangle over here and there's a triangle over here. Are they the same? And we got to justify our answers. Now, I don't remember how much, I don't know how much you remember from elementary math, or if you did this at all. But when you're looking at triangle angles, if you've got 2 interior angles like this, they are equal. So that is actually the same as that. And it's also a rule, and it's also a law, that that this angle here is the same as this angle here, and this angle here is the same as this angle here. There's a theorem that deals with that, and I can't remember what it's called off the top of my head, but let's just say all of the angles are equal. Not equal, they're corresponding. But you have to be careful which angles you're looking at. So angle Q, and that's how you write angle, it's just like the little less than sign looks like. So angle Q is the same as angle S. For angles, you can either call it RST, so RST could only refer to this angle, or TSR could be that angle, okay? But oftentimes, if there's just a letter there, you will refer to it as angle, whatever the letter is. So angle Q must be the same as angle S, and any scratches there. And what else do we know? We know that this angle. Now this one's where we got to be a little careful because the R could be referring to the angle here or the angle here or either of these two. So let's refer to these ones a little differently. Let's refer to this angle here as TRS. So angle TRS can only be this guy. So angle TRS needs to be the same as angle QRP. So we got to be a little bit more specific on that one. And then the last one, we don't have to be specific again. So angle P, so that's this one, is going to be the same as angle T. So our angles are corresponding, which is half the battle right there. It's the easy half of the battle, unfortunately. So maybe it's technically not half the battle, but it's one of the two things we need to check. Now we've got to check the sides. And the sides scale factor, or the ratio of the side lengths, has to be the same. So we have to just make sure that we're dealing with corresponding sides. And I'm going to name them triangle 1 and triangle 2, just to make things a little easier for me to differentiate. Why am I doing that? Because if I'm making a fraction, if I put a number in the numerator from triangle 1, that means the denominator has to be from triangle 2, and I have to keep that order the whole way. So I'm going to start with triangle 1, and I'm going to start with line QP. Okay. So number 1 is always going to be on the top, or the numerator, and number 2 is always going to be on the bottom, or the denominator. So let's look at our first line. Our first line is going to be QP over, okay, now what is QP? Okay, what is this related to? It's between the square and the dot. Well, between the square and the dot is clearly line TS. Okay, so what is that? QP is 4 and TS is 6. So 4 divided by 6 is 2/3. So that's 0.667. I will round it. Okay. What is this? Meters? No, that's not meters. That is the scale factor. Okay. Scale factor does not have a unit. So that is the first side that we checked, and it actually didn't prove anything because we've got nothing to compare it to. So we've got to keep doing that for the other two sides. All right, so we did QP and TS. What are we going to check next? Doesn't really matter. Let's check PR. So let's do PR. Remember, it's got to be something from number 1. It's got to be on the top. Otherwise, we can get some false data. So something from number 2 needs to be in the bottom, or the denominator, and it's got to be the corresponding side. So PR is between the square and the x, and that's why I label the angles this way. So between the square and the x. Well, between the square and the x is TR. Okay. And PR is 5 meters, and TR is 7.5 meters. So we should hope we're getting 0.667 on this one as well. So we got 5 divided by 7.5 equals, yes, 0.667, which is the scale factor, which means the ratio, and a ratio is just a fraction, right? A ratio of QP to TS is exactly the same as the ratio of PR to TR. And then let's check the last one, because triangle, so we got 3 sides, and the side we haven't checked is, must be the QR. And QR is between the x and the dot, so between the x and the dot is ST. So QR is 6 meters and ST is 9 meters. And we can already tell that that is, if you divide both of those by 3, you get 2/3, which is the same as what you get here, right? Divide both these by 2, you get 4. 4 divided by 2, you get 2/3. And down here, you get 2/3 as well. So we know it's going to be. So we have proven, okay, by the way, 3 dots means therefore, which is what that's what the 3 dots mean. When you do proofs in science or math, you learn all these little shortcuts, so you don't have to write out long words like therefore. So therefore, triangle, and by the way, the way you represent a triangle is the same way as the way you would represent an angle. You could say triangle RQP, or you could call it triangle PQR or PRQ, but I labeled them 1 and 2 just to make it a little easier. So triangle number 1 is similar to triangle number 2. And if you say, you don't know which one of these is the original, so you can't really say whether it's an enlargement or reduction. And in fact, it might be neither. It might just be two random triangles beside each other. But what we do know is because all the angles, the interior angles are the same, and because the ratios of all the sides between the two triangles are the same, we could say without doubt that triangle number 1 is similar to triangle number 2. How can we use this in the real world? Okay, you're going to see a lot of shadow questions and a lot of angle questions about, building sizes and where planes are in the sky and things like that. So let's just give an example here. At a certain time of day, a person who is 1.8 meters tall has a shadow of 1.3 meters. Okay, so I always love to draw these because it helps me visualize the problem. There's the sun. And the sun beats down at an angle. Okay, so let's just say the sun comes down at an angle and throws shadows on the ground. Here is a human. Okay, so whatever, it's a boy, a girl, it doesn't matter. Okay, but it's a person. Okay, it's a person, and they are standing on the ground, and their shadow is cast. Okay. So the shadow on the ground says the person is 1.8 meters tall, so that is 1.8 meters right there, and the shadow is 1.3 meters, so there's the shadow. At the same time, the shadow of a totem pole is 6 meters long. So under the same sun, we can also have a totem pole here, and I'm not going to try and draw a totem pole, but I'm just going to draw a pole. Okay, and the totem pole, we don't know how tall it is, so I'm just going to call it X. But it says that the shadow of the totem pole is 6 meters. Now let's just be careful because these two triangles kind of share each other. So it's not 6 meters to the person, it's 6 meters for the whole shadow. Okay, so the person's shadow overlaps the totem pole's shadow a little bit. So what we've got here is we've got two triangles. We've got a triangle number 1 there, and then the bigger one, the one that goes all the way out here, is number 2. And I might even just kind of draw over that in red just to demonstrate that there are two different triangles here. So this is sort of the big triangle that covers the whole totem pole, and then this is the triangle that just deals with the human. But you would agree that those are two triangles. At least I hope you would. Triangle number 1, triangle number 2. Now, clearly, they share that angle right there. Okay? It's the same angle. They also share this angle because it's got to be 90 degrees. We're assuming the person and the totem pole are straight up. If you have two angles that are the same in a triangle, two angles that are the same, or that are equal, in a triangle, the third one is also equal. I'm not dealing with one triangle, I'm dealing with two triangles. If you have two angles that are equal in two triangles, the third angle is also equal. That wasn't really part of the question, but you need to know that all the angles are equal. Well, we know that this one's 90 for both of them, and we don't know what this angle is, but we know it's the same because it's literally the same end of the triangle, which means whatever this is up here, okay, so at the end of that, whatever this is up here, it's the same as what this is right here. And we don't know what that angle is because we don't know what the other angle is. But the fact that all triangles have 180 degrees in them means that if two of them are the same, the third one has to be the same too. If they gave us one of the angles, if they gave us this angle, we'd be able to figure out this angle because we know this one's 90. And the other way around, if they gave us this one, we'd be able to figure out this one. But they didn't, and we don't need to know it. So what do we need to do? We know that these two triangles are similar. And what we need to do is we need to figure out x based on what we know about triangle 1. Okay? So we have enough information to do that. We just need to find out what the scale factor is. So the scale factor of these two triangles, okay, is always equal to the side from the new version over a side from the original version. In this case, you just got to pick which one you want to be the new and which one you want to be the original. It doesn't matter. I'm going to pick the person to be the original one. Okay, so I'm going to go O is person, and what that means is let's look at the 1.3 meter length for shadow, and then 1.8 meters tall. Okay, so we've got two pieces of data there if we say that the person is the original. So let's figure out what the scale factor is first. So the scale factor is going to be equal something from the new over something from the old. Well, what do we have together? Okay, we've got the new length of the shadow. So we're going to deal with the length of the shadow, okay? So like this is the length of the shadow, and I'll put prime to recommend it, to note that it's the new one. And we have to put that over the corresponding side or line, which would be the length of the shadow originally. So what two numbers correspond with the lengths of the shadows? The length of the shadow for the original is 6 meters. The length of the shadow for the new is 6 meters. For the original is 1.3 meters. Okay, so our scale factor is 6 divided by 1.3, which is let's call it 4.6 meters. It says nearest tenth of a meter. Okay, so it's 4.6, no unit, because this is just our scale factor, 4.6. So we know two things already. We know that these triangles are similar. Okay? We know they're similar, and we know that they have a scale factor of 4.6, which means that the bigger one, number 2, is 4.6 times the size of number 1. If we have a measurement and the scale factor, we can figure out the other measurement. So the height of the person corresponds to the height of the pole, which is what we're trying to figure out. Okay. So let's just use our scale factor to figure out the last piece of this project. It's still scale factor equals new over old, but this time instead of trying to find the length of the shadow, we need to try to find the height of the totem pole. So our scale factor is 4.6, okay, equals, remember we got to start with the n, so n is the second triangle. That's the thing we don't know, is the x for height. But we do know the height of the original, which is 1.8 meters. Okay. Now we've got the proportion, fraction equals fraction. We have 3 pieces of information, which means we can solve for the fourth, and then it's just cross multiply and divide, right? So it's going to be 1.8 times 4.6. Okay, so x equals 1.8 times 4.6. And then divide that by 1, which we know we really don't have to do. So 1.8 times 4.6 is 8.28 meters. So what that means, we solve for x, it's 8.28 meters. Because it's a word problem, we should put a concluding sentence in here. So we should say the totem pole is 8.10th of a meter, it said? 8.28, so that's going to be 8.3 meters tall. Always look for the rounding. All right. Now we can check this, or we could have done it a different way. I just want to indicate, another way of doing this, but I don't want to take away from the first one. We could set this up if we know that these are similar triangles. we can set up a direct ratio because we said the scale factor equals n over O. Well, we also know that the scale factor would be the same for, so 1.3 relates to 6 meters, right? So we could do 6 meters over 1.3 equals the height of the new one, which is x, over 1.8. So we could have gotten the exact same result as doing this work here by just plugging it directly into the ratio. So, you know, it's new on top, old on the bottom. So new length of shadow over old length of shadow equals new height of totem pole over old height of person. So as long as you've got the news up top and the originals on the bottom, you could have just solved this directly. And this is a good way to check, right? So 1.8, you've got to cross multiply. 1.8 times 6 equals 10.8. So this would be x equals 1.8 times 6. That's the cross multiply. And then you got to divide by the only other number, which is 1.3. And what we get is 10.8 divided by 1.3 equals 8.3. So this is, this would be a short-circuited way of doing it. As long as you understand the concept, I'm perfectly comfortable with you just setting up your ratios and then solving it directly. But this way, I think it's a little bit more organized, and it forces you to write out what you know and what you don't know. But it's a great way to check, right? You should get the exact same answer if you figure out the scale factor first and then use that to figure out the height. You will get the exact same answer as if you just put in the ratio of the two sides, because they have to be equal. Reflections and line symmetry. 7.5. That'll be another lesson. So hopefully you've got enough information to do the practice questions from 7.4 from the textbook. And as always, if you have any questions or concerns, or you have a little trouble drawing these or identifying what the triangles are or which sides are corresponding, please send me an email. I'll do my best to help you out. Have a good day.